It's one small step for man, one
I came across one of these popular Lithophane Moon Lamps, and it seems like a fun challenge to recreate one using Arduino and incorporate some sensors to enhance its interactivity. Actually, before we start, let me explain what a lithophane is. Lithophane sounds like a modern word, but it is actually an art form that originated in Europe in the 19th century. It is a type of artwork created from a very thin translucent material such as porcelain or plastic. When backlit, the varying thickness of the material displays a detailed image or scene. The original technique involves carving or molding the material so that it is thicker in some areas and thinner in others. Lighter areas allow more light to pass through, while darker areas are thicker, blocking more light. This creates a beautiful effect, revealing the image in gradations of light and shadow. The easiest way to create a lithophane from an image is by using a 3D printer. And there is a free website where you can just upload an image and it generates the STL file for you. Here I have a funny picture of our dog Lacey. I removed the background and uploaded it to this website. Then I downloaded the file and printed it out. It's crucial to remember that to achieve the desired effect, you should print the object with 100% infill. As you can see, some areas are thinner than others, allowing more light to pass through, and vice versa. I came across this repository on Thingiverse where this guy has crafted a lithophane replica of the moon using real color and elevation data provided by NASA. The STL files are available in various sizes and I choose the 6-inch version for my project. Now let's talk about the functionality of the lamp. I'd like the lamp to be interactive. So a gentle touch will toggle its state between on and off. To make the lamp more interesting, it would be nice to have it changing colors. So for this purpose, we could use a single tap gesture for changing colors. Finally, a double tap will switch the lamp to auto mode, where it automatically will turn on and off based on the ambient light. So as it gets dark, I'll have my own moon rising in my room. Now that I have an idea of what I'm trying to achieve, I need to find a way to put all the electronics inside the sphere. The problem is that I only have it in STL format and Fusion 360 cannot handle the conversion into a solid body without crashing. Thus, I need to find a workaround. So what I am thinking is to split it in two pieces using the slicing software of my Reality printer, having the second part small enough so that the seam where the two pieces join is not obvious, but big enough so that I can place the LEDs and the electronic components. The smaller part is simple enough and I was able to convert it into a solid body and edit it. I modified it by adding a hole for the power supply jack and I'll attach the core to it as well. Inside the core I'll store all the electronic components and the Arduino to prevent them from casting shadows on the interior of the sphere. On the outside of the core I'll attach the LED strips and aluminum foil, which will serve as a capacitance sensor for the touch gesture. The first part came out pretty good, but to be honest this was my third attempt. The trick was to use a bigger raft to stabilize the part while printing. Alright, now that we have all the parts printed out, let's focus on the electronics. The first thing I need to figure out is how to control the LED strips that I've chosen for this project. I've opted for the simplest and most popular version, the SMD 5050, which are analog RGB LEDs, not individually addressable. This means that the entire strip always displays the same color. The strip has 4 terminals, a shared 12-volt supply, and a separate return paths for green, red and blue. It can be cut at designated lines, exposing paths for soldering wires. Each segment consists of 3 50/50 chips. Each chip contains 3 LEDs, one for each individual color. To turn on one of the color channels, the corresponding return path needs to be switched to the supply ground, closing the circuit and allowing current to flow. These segments are repeated along the length of the strip, all connected in parallel. The return path can carry a significant amount of current, approximately 50 mA per segment. For the Moon Lamp project, we'll need 8 segments times 50 mA each, which can go up to 400 mA at its maximum. For our project, we'll be using the IRF 520, an enhancement mode N-channel MOSFET. Now, let's continue with a simple circuit by connecting one channel of our LED strip to a 12-volt power supply. By adding a switch, we can control it manually. And by varying the voltage, we can dim the light. That's great, but how can we automate this with Arduino? This is where MOSFETs come into play. If we place a MOSFET between the power supply and the LED strip, the LEDs will remain off until we apply voltage to the gate pin of the MOSFET. Let's give it a try with a simple circuit. We need to connect the positive wire of a 12-volt power supply to the 12V pin of an LED strip. Next, connect the negative wire to the source pin of the MOSFET and the drain pin to the green light pin of the strip. Additionally, we need another wire for the gate pin. The circuit should look like this. Notice that the light is off. However, if we connect the gate pin to the 12-volt supply, it activates the MOSFET and the light turns on. When we disconnect the voltage from the gate pin, the light remains on because the MOSFET is now latched. The gate terminal acts as a capacitor and stores charge, which has nowhere to go, causing the MOSFET to remain activated. To deactivate the MOSFET, we need to discharge the gate terminal by providing a path to the ground. But how is this related to our project? As mentioned earlier, the Arduino cannot directly supply and control varying voltage levels. Instead, it uses a technique called PWM or pulse width modulation. This technique is implemented through specific pins on the Arduino that produce pulses or signals rather than a continuous variable voltage. The amount of time the pin is on versus off determines the effective voltage or power delivered to a device like an LED. The percentage of time the pin is on is called a duty cycle. The frequency of the PWM is the rate at which the pulses are repeated. On Arduino, the default frequency for PWM pins is about 490 Hz. Except for pins 5 and 6 on some boards, which have default frequency of about 980 Hz. Using the function analog write, we can control the PWM duty cycle on a pin. At 0% duty cycle, the pin is always off. At a 50% duty cycle, the pin is on half the time and off half the time, simulating about half the maximum voltage. On a 100% duty cycle, it is always on, which corresponds to 5 volts on a standard Arduino. These PWM signals can be amplified using a MOSFET to control devices with higher voltages, such as our 12-volt LED strip. By adjusting the duty cycle, we can control the brightness of the LEDs. Longer duty cycles make the strip brighter, while shorter duty cycles make the strip dimmer. There is something we need to be especially careful about. As I demonstrated in the last experiment, the gate pin must be discharged in some way to turn off the LEDs. When connected to the Arduino, the state of the gate pin changes multiple times per second. This rapid switching from off to on results in a large inrush current that needs to be managed to prevent damage on the Arduino. To manage this, we need to add a resistor to limit the current. To discharge the MOSFET, we need to provide a path to ground. However, directly wiring it to ground is not feasible because the current would still be too large. Therefore, we need to add a pull-down resistor. When the Arduino energizes the gate pin, a small current will flow through this resistor while the MOSFET gate pin receives the full voltage. When the pin is de-energized, the stored electrons can safely escape to ground through the pull-down resistor. Enough theory, let's build a prototype of our moon lamp circuit. We start by creating paths from the 12 volts power supply, which will power up both the LED strip and the Arduino. I'll show you how this will be done in a moment. Next, we connect the 5 volts input/output and the ground to separate paths. But we need to ensure that both grounds are shared for proper operation and communication between the components. Then we add 3 MOSFETs, one for each color channel. To connect the gate pin of the red channel to the D11 pin of the Arduino, we add 1 kΩ resistor and 10 kΩ pull-down resistor as I explained before. And I repeat the same with the green and the blue channels. The 12 volts pin is connected directly to the 12 volts power supply. Next, we connect the capacitance sensor, which in our setup will be a simple piece of aluminum foil, to pins D2 and D4 along with 1 mega ohm timing resistor. This configuration is used to measure changes in capacitance by controlling the charge and discharge time of a capacitor. The sensor's plate and the human's body form a capacitor which stores electrical charge. The Arduino is capable of measuring this charge to detect touch or proximity interactions. We connect the light sensor to analog pin A2 and the piezo speaker to pin A1. In addition to playing sound, the piezo speaker can also be used in reverse manner to detect vibrations such as taps or knocks on a surface. Finally, to power up the Arduino Nano, we need a 5 volts supply. To reduce the 12 volts to 5 volts, we use a voltage regulator, along with a small capacitor to filter out any noise as recommended by the manufacturer. And now, let's give it a try. When I touch the foil, the lamp turns on. Touching it again, the lamp turns off. Now tapping on the piezo speaker should change colors. A double tap activates the auto mode. Now to check the photoresistor, I'll turn off the lights in my garage and the darkness should activate the LEDs. Finally, when I remove the USB cable, the Arduino should continue to be powered by the voltage regulator. Everything works, so let's don't waste more time and build the real thing. But before that, let me show you how the Arduino controls everything. We start by defining of all the pins needed. Then we set some threshold values as constants. If some of the sensors needs fine-tuning, this is the place where they can be configured. During the first 2 seconds after the Arduino boots up, we calibrate the sensors to determine their base values when we don't interact with them. For this reason, it's important not to touch the lamp during that time. Inside the loop, we check the capacitive touch sensor. If we detect an interaction, we put some timeout period to prevent multiple detections. Then we check the tap sensor. The logic responsible for a double tap is a bit tricky. Basically, we give it some time during which we wait for a second tap. If this doesn't happen, we count it as a single tap. If the auto mode was set with a double tap, we check the light sensor value to toggle the light depending on the environmental light. And here is the coolest feature in my opinion. We constantly monitor the environmental light and readjust the optimal brightness of the lamp. So, if there is some light around, it will be brighter, and if it's completely dark, it will dim to look more realistic. I prepared the Arduino to be attached to the rest of the components. Here are the RGB outputs, the pins for the capacitive touch sensor, the light and the tap sensor outputs, the 5V and the ground pins. We will supply power to the Arduino through the 5V pin, so we need to attach the voltage regulator next to the MOSFETs. Alright, now we're ready to connect these pieces together. I will attach wires to the RGB outputs. Next, let's connect the tap sensor here and the light sensor next to it. Now we have the piezo and the light sensor connected along with 4 wires for the LEDs. Here are the wires for the 12V power supply. The whole assembly should go into the core like this. The piezo speaker will be glued on top to sense vibrations caused by taps. On the outside, I'll attach the LED strips and the aluminum foil responsible for the touch gesture. Let's cut out the RGB strips. They are self-adhesive and will be placed right here on each side of the core. This wire will connect the aluminum foil to the Arduino. Let's do a quick test. It turns on and off and changes colors. Now let's test the auto mode. Finally, I will disconnect the USB cable from the Arduino so it will be powered by the voltage regulator. The next step is to solder the LED strips on each side. We need 4 pieces of these wires on each side. We need to put some order in this spaghetti ball of wires. The last piece is the touch sensor and the foil which I have attached to this wire. Oops, it's a bit short, I'll fix that. Next, to cut out the foil pieces, I prepared a 3D printed pattern. I'm attaching them to the sides of the core with some glue. It's important to have the plates touching the wire, so we shouldn't apply glue on it. This is how it looks at the end. It looks like a real space satellite. This is a 12-volt socket for the power supply. We need to insert it into the bottom part of the lamp and then solder it to the wires. So far, so good. Now that we have the core prepared, we need to insert it into the sphere. But before that, we need to make a hole at the top of the lamp for the light sensor. I used a 4.5mm drill. To pull the sensor out from the hole, I used a standard thread. To set it in place, I used some hot glue. The bottom part is a snap fit, but some hot glue can be applied if needed. The final part is the stand. We need 6 pieces of wood that I cut out from this batten, which I got from the hardware store. To assemble them, I'll use hot glue. To make the whole construction stronger, I'll drill some holes on the side and the other end, right in the middle where each pair of pieces will join together. I'll repeat this for all of them. Here I applied hot glue right in the holes and then pressed the 2 pieces together. Then, with the help of this tool, I ensure the 90-degree angle. This type of construction is simple enough but becomes pretty stable for the purpose once the glue has hardened. And here it is, our stand for the moon lamp.